Address Resolution Protocol, more commonly referred to as ARP, is the IPv4 mechanism for bridging Layer 2 Ethernet addresses with Layer 3 IPv4 addresses. This process is required to route packets from one host to another host on the same Layer 2 broadcast domain. My name is Graverose and this is dotPCap, the quick video series where we examine networks at a packet level. First and foremost, these videos will never be monetized, so you should never see ads on them. If you appreciate the content and want to make a donation, links are in the description. If you aren't able to donate or just don't want to, that's fine too. Knowledge should be free. With that out of the way, let's dig into ARP. ARP is a protocol sometimes referred to as Layer 2.5 since it has characteristics and features on both Layer 2 and Layer 3. When a machine on a subnet wants to send a packet to another machine on the same IPv4 network, the first thing that happens is ARP. The client, or sender, sends out a specific packet called an ARP who has packet asking who owns the IP address the client is trying to reach. The client will send this packet out with its own Ethernet address as the source and the broadcast Ethernet address as its destination. This destination is indicated by the address being all Fs and will be received by all hosts on the same Layer 2 broadcast domain. This could be contained to a dump switch, or it could span across multiple devices with a linked VLAN. Whoever owns the IP address the client is looking for should be the only one to reply to this message. The reply message is not a broadcast message but a unicast message directed back to the requesting client with the sending Ethernet address belonging to the owner of the IP address. Here's a simple analogy. You're in a room full of people you don't know, but you do know that you need to speak with a person named Steve, so you shout to everyone in the room, "Hey, whoever Steve is, please come introduce yourself to me." Steve then walks over to you, and you can now begin speaking with one another. I'll be using this analogy a lot since networks operate in this fundamental manner. All operating systems have an ARP cache, which is a listing of Ethernet addresses mapped to IPv4 addresses, which is valid for a set amount of time depending on the operating system. This makes sure that network utilization is kept to a minimum, since broadcasting ARP requests for every packet would likely cripple a populated network in a short amount of time. Once the operating system has run its timer for the ARP cache, it will then send out another ARP request the next time it needs to speak with that host. It is possible to set static ARP entries on devices, which mitigates the requirement to send out ARP packets. However, this can cause issues when replacing hardware or in terms of managing a large list. There are times, however, that static ARP entries are required based on the provisioned hardware and interoperability of different devices. Just remember to document any static ARP entries you have in your environment, since these are often overlooked when troubleshooting issues. Gratuitous ARP packets can also be sent out by machines to ensure that all Layer 2 connected devices have Ethernet to IPv4 address mappings stored of the gratuitous ARPing machine. This type of broadcasting will bring latency down by a small margin since machines won't have to send ARP who has packets for specific hosts, however it will increase the amount of broadcast usage on the network. In 2019, when this video was made, the amount of resources on networking equipment is very minimal with regards to processing gratuitous ARP packets. It is possible to use ARP poisoning to perform attacks, such as man-in-the-middle attacks as well as denial-of-service attacks, by responding to ARP requests where you, the attacker, are not the intended responder. Let's say, for example, you're on the IPv4 network 10.20.30.0/24, and the default gateway of the network is 10.20.30.1. As an attacker, whenever an ARP who has packet shows up requesting 10.20.30.1, you can reply to that with your own Ethernet address and hosts will send their gateway traffic to you. You can then route it and perform a man-in-the-middle attack, or just drop it and prevent anyone on that network from accessing the gateway, thus denying them of a service outside the local network. These are two very basic examples, and there is a lot more to successfully executing these attacks, but I'm sure you get the idea. This isn't a pen test or red team video, so if you want to experiment with these type of attacks, I suggest getting VirtualBox and a few virtual machines to lab this out. Maybe I'll do a future episode on this topic later. Let's take a look at the packet capture command that we ran. On Linux, tcpdump is the name of the command we're running. The first command line switches we're using are -nn, which tells tcpdump not to resolve host names or service names. Next is -vvv, which is to provide as much verbosity as possible. The -e flag lets us see the Layer 2 Ethernet headers. By using -s, we can set the snap length, which tells tcpdump how much of the packet to capture. By setting this to 0, we effectively capture all the packet regardless of the size. The $X flag will output a hexadecimal on the left-hand side with byte counts and ASCII on the right. We then use the -C flag to tell tcpdump to only capture 100 packets, at which point it will automatically stop. The last switch we use is -I and the name of the interface to capture on, in this case WLAN 0. After the command we have our Berkeley packet filters, or BPF for short. The BPF to capture ARP packets is just the word ARP. The last thing to keep in mind is that even though ARP bridges layer 2 and layer 3, fundamentally it is a layer 2 protocol, which means that ARP packets will never cross a layer 3 routing interface. That's it for now, but please check the description for links to my packet capturing tool at tcpdump101.com, as well as social media and donation links. Feel free to like and subscribe, but don't feel that you have to. Happy packet hunting.